Hello, everyone. I'm Kazutoshi Tanaka from Omron Cynic X Corporation. Today, I'd like to introduce a plastic tabletop cable-driven robotic arm with all motors located at the base link. First, I'll introduce the overview of this study. To develop a lightweight cable-driven robotic arm, we focus on locating all motors at the base link and using structural parts. Locating the motors could increase the number of force transition parts. Using plastic parts causes the cable coming off. We propose a cable path design and a compact cable pretension mechanism to decrease the number of parts. We also propose covering parts to avoid cable coming off. In experiments, we evaluate the robotic arm that we developed, verifying its basic performance and its capacity for executing fast motion tasks and contact-rich tasks. Let me explain the detail. First, I'll describe the background. Tabletop robotic arms have been used for education and research. As you can see in this slide, such arms have been developed in research and are commercially available. We aim to decrease the weight of such arms more because being lightweight is important for safety. Which mechanism suits a lightweight robot? As you can see in this slide, a cable-driven mechanism has been used for lightweight robotic arms. This mechanism decreases the weight by locating motors near the base link. In this study, using the mechanism, we aim to decrease the weight by focusing on 2 points. The first point is locating all motors at the base link. As you can see in this slide, by locating all motors at the base link, Endo and his fellows developed a 10-meter super-long lightweight cable-driven robotic arm. The second point is using plastic structural parts. As you can see in this slide, by using plastic structural parts, Tanaka and his fellows developed a lightweight humanoid robot that jumped and hit a ball in the air. Locating all motors at the base link and using plastic structural parts decrease the weight of a cable-driven robotic arm but cause 2 issues. Next, I'll explain these issues. The first issue is increasing the force transmission parts and the weight. Locating all motors at the base link can decreases the weight. But as you can see in this slide, the locating requires many parts to transmit the force of motors from the base to far joints. The second issue is the cable coming off. Plastic structural parts can decrease the weight of an arm. But plastic structural parts are softer and bend more easily than metallic parts. So, as you can see in this slide, the bending of structural parts causes cable coming off from a pulley. We overcame the 2 issues by focusing on 3 points. I'll explain these points. The first point is the cable path design. As you can see in this slide, other cable-driven robots use parts to add tension to a cable. Then, the cable paths of these robots curve. We removed such parts to decrease the force transmission parts. Then, the cable paths of our arm are straight. Instead of the parts, we adopted a compact cable pretension mechanism. The second point is this cable pretension mechanism. As you can see in this slide, this compact mechanism adds pretension to a cable by reeling this and fixes the cable to a link by inserting a pin. The third point is its covering parts to avoid cable coming off. As you can see in this slide, joint parts cover pulleys. So, if a cable is slacked once, this cable can go back to a pulley by being covered. Before moving on to the next section, I'll introduce the control of the arm using this slide. The arm controls its motor velocity based on the target hand velocity. As you can see in this slide, it calculates joint velocity from the target hand velocity at first. Next, it also calculates motor velocity from the joint velocity based on their relationships. As you can see in the slide right, the cable velocity connects the joint velocity with the motor velocity. We evaluated the robot in experiments. Next, I'll explain the experiments. This video shows our experiments to evaluate the developed arm. We evaluated its response speed and accuracy of hand position control as basic performance. Also, the arm executed contact-rich tasks and fast-motion tasks to demonstrate its advantage. The robot successfully executed contact-rich tasks and fast-motion tasks. Let me summarize this presentation. We presented a plastic tabletop cable-driven robotic arm with all motors located at the base link. Experimental results indicate that this arm can execute contact-rich and fast-motion tasks. Future work is to develop a design optimization method and another method for learning manipulation leveraging contact. That's it. Thank you for listening.